Now, like I said, this is my hyperbola. This is my expression as x squared by a squared minus y squared by b squared minus 1 is this expression as s equal to 0 will represent a hyperbola, right? And this is my expression t, which is xx1 by a squared minus yy1 by b squared minus 1. It is my expression s, this is my expression t. And if x1, y1 be a point on the hyperbola, then t equal to 0 will represent the tangent. However, if x1, y1 be a point outside the hyperbola, like if x1, y1 be a point outside the hyperbola, then from points outside the hyperbola you can draw two tangents to the hyperbola. PQ and PR are the two tangents you can draw from an external point. From an external point you can draw a pair of tangents to the hyperbola. And this QR is called a chord of contact. With respect to P. Chord of contact with respect to P. And like before, if x1, y1 is outside, then the equation of the chord of contact would be t equal to 0 would be the equation of the chord of contact. Right? We've seen this before. Also, if I have any chord, internal or external, and M be the midpoint of that chord, M be the midpoint of that chord, then the equation of the chord in terms of midpoint is given by t equal to s1, right? I'm not redoing this. T equal to s1 is the equation of the chord in terms of the midpoint. So this is just the way it has always been. Just the way it has always been. Now, let me tell you a very important thing. Two branches of a hyperbola. Let me not draw this. These are two branches of a hyperbola. All right. This is the inside, and this region is the outside of the hyperbola. If you are given a point outside, you can draw two tangents to the hyperbola. Whether those two tangents belong to the same branch or belong to opposite branches is important to understand, right? So I could have a point here, and from this point there will be a tangent like this to the hyperbola, and there is going to be a tangent like this to the hyperbola. Two tangents. These are tangents drawn to opposite branches. So there are certain points from where you can draw tangents only to the two branches separately, not to the same branch. Not to the same branch. And there are points P from where tangents are drawn to the same branch of the hyperbola. Tangents are drawn to the same branch of the hyperbola. How would you know from, where is this point located and where is this point located? Both are outside the hyperbola, but some points in the outside will be such that you can draw tangents to the same branch. Some points you will draw tangents to opposite branches of the hyperbola. So let me tell you when it happens. These are the two asymptotes. These are the two asymptotes to the hyperbola. These are the two asymptotes to the hyperbola x squared by a squared minus y squared by b squared equal to 1. Now let me tell you this plain and simple. There is a region like this, which is on the outside but lies between the asymptote and the two branches, right? The shaded region, right? And there is also a region, like this shaded region. These are two kinds of shaded region, right? These are the two shaded region between the asymptotes and the curve, right? And there is this another region which is simply the region between the asymptotes alone, right? This entire set is called region 1. This entire set is called region 2, R2. Let me tell you that if you select points in R1, if you select any point in R1, whether this or this, then you will draw tangents to the same branch. You will draw tangents to the same branch. If you select any point in this region, you will draw tangents only to this branch. If you select any points in this region, you will draw tangents to this branch alone. But if you select a point in this region, say P, then tangents would be drawn to opposite branches. Tangents would be drawn to opposite branches. Do you understand what I'm saying? For points in this shaded region, tangents will be drawn to the same branch of the hyperbola from. Try and prove it yourself. Try and prove it yourself. But if you take points in this region, then tangents will be drawn to opposite branches, the pair of tangents. What's the difference? If from a point P, the tangents drawn are to opposite branches. If from a point P, tangents are drawn to opposite branches, that means like this. If tangents are drawn to opposite branches, that is like this. Then these are the points of tangency. This is a special point where the tangents drawn are to opposite branches of the hyperbola. Then this becomes my chord of contact. QR becomes my COC, chord of contact. QR becomes my chord of contact. And do you realize, in such cases, the chord of contact is an external chord. In this case, the chord of contact is an external chord. Whereas, if I take a point in this region and I draw tangents, then tangents would be to the same branch. And I urge you to prove this. And QR then would be the chord of contact, but it's going to be an internal chord, right? It's going to be an internal chord. The tangent is, the chord of contact would be an internal chord then, right? Now, how would one know whether, suppose I give you the equation of a chord. By looking at it, how would I know if it's going to be an internal chord or an external chord? First of all, how would I even know that it's a chord? It may not intersect the hyperbola anywhere, right? It may not intersect the hyperbola anywhere. Now let me tell you, if y equal to mx plus c be a chord, if y equal to mx plus c be a chord, hey, do you recall all of this? In a circle, x squared plus y squared equal to a squared, and I have a chord y equal to mx plus c. Then, do you recall, if this is a chord, then c squared less than a squared into 1 plus m squared. Recall this? C squared has to be less than 1 plus a squared. C squared equal to a squared into 1 plus m squared will give me a tangent. C squared less than a squared into 1 plus m squared will be a chord. That's for a circle. For a parabola, y squared equal to 4ax. If this is a chord, then c equal to a by m would be a tangent, and c less than a by m will be a chord. C less than a by m will be a chord. For an ellipse, x squared by a squared plus y squared by b squared equal to 1. C squared equal to a squared m squared plus b squared will give me a tangent, but c squared less than a squared m squared plus b squared will give me a chord. C squared less than a squared m squared plus b squared will give me a chord for this. In a hyperbola, things change a little bit. For this to be a chord, it must intersect the hyperbola at two distinct real points. When will this be a chord? If this intersects the hyperbola at two distinct real points, right? That means when I solve these two equations, then I should get two distinct real roots. That means that's when this is going to be a chord, right? So x squared by a squared minus, in my attempt to solve these two, writing y as mx plus c is 1. This should give me two distinct real values of x. Right? So 1 by a squared minus m squared by b squared into x squared minus 2cm by b squared into x plus minus c squared by b squared plus 1 equal to 0. The two roots of this must be real and distinct, because this will give me the x coordinates of the two points of intersection of this line with this curve, right? When will that happen? For this to be a chord, the discriminant of this will be greater than 0. For this to be a chord, the discriminant of this must be greater than 0. This will now, let me tell you, if you do this, you'll get c squared greater than a squared m squared minus b squared. In all other cases, it turns out to be c less than something. In a hyperbola, you'll get c squared greater than a squared m squared minus b squared is what you'll get in a hyperbola. This is what you'll get in a hyperbola. This is what would give you a chord. But this chord could be an internal chord or could be an external chord. How would one know if a chord is internal or if a chord is external? How would one know that? Right? Surely if this happens, this is a chord. If this happens, it's a chord. It will intersect the hyperbola at two real and distinct points. But how would one know if it's an internal chord or an external chord? Look, what's the difference between an internal chord and an external chord? That's important to understand. This is a hyperbola, right? If this is an internal chord, right? This PQ is an internal chord. P has coordinates say x1, y1, and Q has coordinates x2, y2. This is a line y equal to mx plus c. This is a line y equal to mx plus c. And c squared has to be greater than a squared m squared minus b squared. C squared has to be greater than a squared m squared minus b squared. That will cause it to be a chord. But when would this chord be an internal chord? Absolutely. Absolutely. Do you realize P and Q are such that x1 and x2 are of the same sign? You see that? x1 and x2 either must be both positive or in this case both negative. है ना? इस केस में अगर internal chord होता तो x1 and x2 will still be positive but both negative. In this case x1 x2 positive and both positive. Right? So x1 and x2 are the roots of this quadratic. Right? So we must have x1 x2 greater than 0 for an internal chord. x1 x2 greater than 0 for an internal chord. That means product of this roots must be greater than 0 for an internal chord. है ना? Product of the roots greater than 0 for an internal chord means what is x1 x2? Product of the roots c square by b squared plus 1 divided by 1 by a squared minus m squared by b squared must be greater than 0 for an internal chord. Yes or no? You know? And this ratio is positive. Numerator is negative. So denominator must be negative. Denominator must be negative. Yes or no? So denominator negative means for an internal chord 1 by a squared minus m squared by b squared must be less than 0 for a internal chord where m is the slope of that internal chord. Where m is the slope of that internal chord. Do you realize you get m squared greater than b squared by a squared? For an internal chord the slope is, that means magnitude of the slope of the internal chord is greater than the magnitude of the slope of the asymptotes. Yes or no? Magnitude of the slope of an internal chord is greater than the magnitude of the two asymptotes. That means any internal chord will be more vertical than the two asymptotes. Any internal chord would be more vertical than the two asymptotes. तो मतलब सोचो, if these are the two asymptotes, the branch, and if I draw an internal chord, can you see visually? Can you see visually that PQ, the internal chord, is more vertical than the two asymptotes? Can you see that? Its magnitude of the slope of an internal chord will always be larger than the magnitude of the slopes of the two asymptotes. They will always be, internal chords will be more vertical than the two asymptotes. Right? Mod m greater than. So this will cause it to be a chord, internal or external. Now if in addition mod m greater than b by a, it will become an internal chord. For an external chord, just the reverse will happen. If this is an external chord, do you see? This is P x1 y1. This is Q x2 y2. That's an external chord. And do you see x1 and x2 are of opposite signs here? x1 x2 for an external chord, EC, not election commission. External chord, right? x1 x2 is less than 0 here. And if x1 x2 is less than 0, just the opposite will happen of what happened here. That means magnitude of the slope will turn out to be less than b by a. That means an external chord will be flatter than the two asymptotes. An external chord will always be flatter than the two asymptotes. An external chord will always be flatter than the two asymptotes. An internal chord would be more vertical than the two asymptotes. This is the condition for a chord to be internal. This is the condition for a chord to be external. This is the condition for a line to be a chord. Now with this input you will be able to show that the region between the asymptote and the curve, if you take a point P, then the chord of contact would be an internal chord, and if you use mod B greater than B by A, you'll realize that that region lies between the curve and the asymptotes. So you know the fact that I stated from points from where tangents would be to the same branch to the opposite branches of the hyperbola.